Begin here. So I want to first thank Chris Lancy from the Hurricane Center for agreeing to do this presentation on tropical cyclone intensity models. So without any further ado, I will turn it over to Chris.
All right, thank you, Dan. All right, so this overview is a combination of a lot of people's work, especially Andrea Schumacher at CIRA CSU in Fort Collins, Colorado. And so this is to get an idea of what are the tools that we use at the National Hurricane Center for making our intensity forecast. And intensity is our terminology for the maximum sustained surface wind. So the objectives for this module, first is know what are the different flavors or different spectra of models that are available for forecasting intensity. What are some of the strengths and weaknesses of each of these types? And then how we use these for intensity forecasting, given the constraints we have at the Hurricane Center as far as time limitations and understanding what the actual intensity is at initial time. A little bit of overview about some of the improvements that are being made on the different models, and then very briefly talk about structure, that is the wind radii forecasting from tropical storm force radius to hurricane force. So it's important to put in context what is this metric that we're calling intensity. And the definition up the top there is max sustained surface wind. And by surface, we're talking about the standard 10 meters or 33 feet above the ground or above the ocean for most of the storms and hurricanes we're talking about. And it's important to keep in mind that this would not include transient features like outflow boundaries or even tornadoes that are embedded within a hurricane. What we're trying to provide with this measure is the representative of the circulation of the cyclone itself. The difficulty is we very, very rarely measure that quantity. 70% of the time in the Atlantic, we're using the Dvorak technique and other satellite measures to come up with the intensity. And Dvorak is actually just a pattern recognition technique. We're fortunate in the Atlantic and occasionally in the East Pacific where we have aircraft reconnaissance, and so that does give you great flight level winds, but nobody lives at 10,000 feet above the ground, and we get high quality surface winds when it's a hurricane. So that's with the SFMR, Step Frequency Microwave Radiometer. It actually doesn't work too well for depressions and tropical storms, so we take a blend of flight level winds and these SFMR winds. And lastly, we do have GPS-based drop wind sondes, but they're just a spot measure, and so we don't put a lot of weight on these, though we will try to launch a couple in the eye wall of hurricanes to assist with knowing roughly how much of the wind is reaching the ocean surface. So you look at how intensity models have been used over time. There's four basic types or flavors of models that are out there. The first is simply based on climatology and persistence. And this one is called the SHIFOR, Statistical Hurricane Intensity Forecast. It was put together by Brian Jarvinen and Charlie Newman back in the 1970s. And it still lives on today because it's a great metric for comparing other methods, whether it's other models, statistical dynamical models, or pure dynamical models, as well as the official forecast. So if we say that we're having less errors than SHIFOR, we have skill. The second type, the statistical dynamical models, where you're taking output from either the global or the regional hurricane models and blending in a statistical regression in that to come up with intensity change. And there's two main ones that we use today at the Hurricane Center, SHIPS and LGEM, and I'll go into detail on all these. And then lastly, the dynamical models. So we have the global models, for example, the GFS, the UK Met Office, and also the European Center for Medium Range Weather Forecasting. So we'll talk about both these types of dynamical models and how they can or cannot be used for intensity forecasting. And lastly is ensemble or a combination of different models blended together. So start off with the basics. SHIFOR is this one based solely on climatology, that is the characteristics of past storms, that we've observed. And persistence, that is, if it's getting stronger, keep making it stronger, or if it's weakening, keep weakening it, based over the last 12 hours. So as I mentioned, it was first developed in the late 70s, and when we went to a 5-day forecast in 2003, this was also extended out to 120 hours. So the predictor days to come up with the combination of climatology and persistence, Julian day, because the annual cycle, especially in the Atlantic Basin, is extremely peaked. So in September, you get half of all the major hurricanes. So if you're closer to September, you have more of a chance to climatologically get pretty darn strong. Also, where is the system forming? We know if there's a system at 40 north, it's not likely to intensify because it's already on its the end of its life cycle, not the beginning. The persistence factor is just what are the peak winds now versus what they were 12 hours ago. And then the motion of the storm as well. Again, if it's moving northward or northeastward, it's very unlikely it's going to intensify at that point. And then a few years ago, a component called Decay-SHIFOR was added to it. So if the track that the SHIFOR model is being used for takes the storm over land, it knows to weaken it, and it's a fairly quick weakening. So this allows one to compare for going over land without as a fair comparison, because if it goes over land, of course, it's going to weaken quickly, and you want to keep that in the baseline. And as I mentioned before, this SHIFOR is something that we compare against. So we don't use SHIFOR forecasting very often, but it's a great baseline, and often it can be difficult to beat. So the statistical dynamical models, one has been around, I think for about 20 or 25 years now. It was developed by John Kaplan and Mark D. Maria, and it's the Statistical Hurricane Intensity Prediction Scheme. And it's a regression model, and so it's looking at predictors from not only climatology and persistence, but also from the atmosphere, and these are based on the GFS fields, Global Forecast System Model fields, as well as oceanic parameters like sea surface temperature and ocean heat content. More recently, in the last few years, they added a component to look at the convective structure using the geostationary infrared imagery to see how symmetric is the convection and how deep is the convection. And lastly, there's also a decay component that is, if the track that you're using this for takes the storm over land, it knows to weaken it fairly quickly. So these predictors, there's some that are most prominent in this regression. The first of which is called a sea surface temperature potential. And it's basically using a top hat function to look at how strong, if everything is perfect conditions, how strong could this hurricane be? So that's called this Vmax versus what it is now. So that gives you the idea of what is possible intensity-wise. So if this parameter is negative, because you're over cold water, usually less than 26 Celsius water, that will be a big negative factor in this regression technique. Another very important factor is vertical shear. We knew that deep tropospheric vertical shear is not conducive for hurricanes to intensify. So once the shear reaches about 15 or 20 knots, between 850 and 200 millibars, that's enough to disrupt tropical storms and hurricanes. The technique also takes into account if you have mid-level shear. Say if the shear is strong between 850 and 500 millibars, often in association with a Saharan air layer jet, then that would be picked up and accounted for as well. The direction of the shear is important too, and that's because if the storm is moving in the direction of the shear vector, then the translational movement of the storm actually reduces the negative effects of the shear. So that's taken into account in this as well. Persistence, again, if it's getting stronger, keep making it stronger. And then lastly, upper level temperatures. We're looking at deep convection driving tropical storms and hurricane intensity. And so if it's colder aloft, you'd have a bit more cape and likelihood for deep convection to continue. The other factors are a little less prominent. Some more of the predictors. There's, I think, the latest rendition has 15 or 20 predictors. The one that's most important on this page is the tendency at 850 millibars for the vortex to spin up in the GFS. So we're moving toward a fully dynamical version of this, essentially, because you're incorporating how much intensification does the GFS model itself see for the vortex. So a couple of predictors that were added a little over a decade ago that helped boost the skill of the model, again, is the infrared imagery. So on the left, you see a very symmetric eye wall depicted in the infrared with very cold cloud tops with the green and the red. So if it's cold in the inner core and it's symmetric, that favors intensification. On the right side, a depiction from satellite altimetry showing the heat content, which is usually calculated as essentially how much energy is available for the hurricane to tap into by considering how deep the water is and how of at least 26.5 degrees C water. So in this case, most of the Gulf of Mexico is warm, but only at the very shallow layers. Below that, it's quite cold. But you have the loop current that comes from the Caribbean into the Gulf, loops back toward Florida as the Florida current, and then often gets these eddies that spin up and contain very deep warm water that can help the intensification process. So if you look at the different predictors and see which ones are most important, again, the ones we talked about, the sea surface temperature potential, the vortex tendency, the shear, and it turns out that the shear is more effective at lower latitudes at impacting the hurricane, persistence, shear direction, the infrared imagery, and on the negative sides, well, you have shear showing up in actually 3 different places here. So it's negative over here and a slight positive over there. And then there's a sea surface temperature potential one. Some of these factors are a little more difficult to directly connect physically to what's going on, but they make sure they test all the possible predictors in a dependent database, and then after the regression's obtained, make sure that it's valid in an independent sample. So the decay over land, show for a storm, for example, like this, Hurricane Dolly, over water was 65 knots. It was forecast by ships to gradually intensify up to 80 knots at 36 hours and then gradually fade. But it was going to be going over land at about 12 hours. And you can see in the red curve what the expected decay would be because of going over land. And again, hurricanes weaken over land because initially you get a reduction of the 1-minute winds because of the increased drag coefficient and friction, but you also get a pretty quick decay because you don't get the moisture fluxes and the heat fluxes over land like you do over water. So I also mentioned about the direction of the shear relative to the storm motion. So down here it shows where would be the most favorable shear directions. So in this case, favorable shear direction where it'd be the shear would not adversely affect the hurricane would be out of the east or northeast. That's because storms in the lower latitudes tend to be moving from east to west, so in the same direction as the shear vector. Conversely, in the higher latitudes, north of about 30 or 25 north, usually the shear vector that's most conducive for hurricane intensification is out of the west because they're moving from west to east. So about a decade ago, a different flavor of statistical model was developed. Instead of a multiple regression approach, it was a logistic growth equation model. And the analogy is that this is similar to how population growth modeling is done. And so it's a differential equation constrained the max winds somewhere between zero, dissipated, and the maximum potential intensity possible, dictated by the sea surface temperatures. And So it does a little better at longer time periods than SHIPS. But it's more sensitive to track errors, and it's a little more difficult to include in persistence. That is it getting stronger now or not? So when we look at which one works better, again, at the shorter lead times, whether it's in the Atlantic in blue or red with East Pacific tropical storms and hurricanes, SHIPS works better out through about 36 to 48 hours, and then LGEM works better at the longer leads from 3 days to 5 days. So we use both. They're using similar similar predictors, but formulated differently. So the way we look at it, and the way that can be accessed by anyone, public or within the Weather Service, is on our FTP site. It's this gigantic printout that is now a page and a half that we look at, and for us it's great because it's got so much detailed information here to really help figure out what is going on now for intensity as well as what may occur. And at the top it shows the actual forecast. So if you just want the bottom line, is it going to get stronger or weaker? The technique also is now providing guidance on is it tropical, subtropical, or extratropical based on the thermodynamics that it's looking at. It's got all the predictors and their change over time, and then the components and how that fits into the ship's output, either a plus or a minus on the intensity over time. There's also technique for rapid intensification index that's led by John Kaplan at the Hurricane Research Division, where it's a probabilistic guidance on how quickly what is the likelihood that a storm may spin up 25 knots or more in the next day. Other guidance in this is the annular hurricane index. If a hurricane is in low shear but moderate SSTs, often they develop an annular type I, sometimes called a truck tire, and those tend to be resilient to change and weaken less quickly than other storms. Another component that was added by Jim Cosson is to look at the eye wall formation on outer eye wall formation. So hurricanes go through concentric eye wall cycles, and so this gives you a heads up of what is the likelihood that a secondary eye wall is going to form in the next day or two. And one thing that's just added this year is if it does develop a secondary eye wall, how much weakening is expected as the outer eye wall contracts in. I know this is a ton of information, but again, it's something that we use and spend a lot of time on each forecast cycle, diagnosing what is going on now and could occur for intensity change. And again, all of these are available on our FTP site. So the global models. We take a look at the Global Forecast System, the European Center for Medium-Range Weather Forecasting, and the United Kingdom Meteorological Office. This year, we're also taking a look at the Japanese global model. We still have access to the Canadian global model and the Navy global model, but don't rely on those nearly as much as these first three. We also have regional dynamical models that are quite helpful. The GFDL model, and I'll go into detail about each of these. GFDN, which is based off the Navy's NavGEM model for boundary conditions, and then the Hurricane WRF model. So I'll go into a little more details about all of these. There is another one that we're taking a look at a little more this year. It's the Navy COAMPS model. It's a coupled model as well. So one limitation, especially in the past, for dynamical models is that the observations in hurricanes, unless they're being sampled by aircraft, are very sparse. So that makes it difficult for sparse data to initialize a strong vortex, especially a mesoscale size vortex like the eye wall and inner core of a hurricane. And then while the regional hurricane models are getting down to just a few kilometer grid spacing, the global models are still on the order of 10 to 30 kilometer grid spacing. And so that's not going to be enough to resolve the inner core of a hurricane. And then the data assimilation is very difficult on storm scale. So even if you get good observations, the folks that are experts in data assimilation are still in the beginning stages of research of how to best take those observations and blend them into the initial conditions. And there's also issues about the physical real different processes, whether it's convection, it's the boundary layer, the microphysics, radiation. So most of these have some parameterizations that are in place, and that becomes more of an issue when you get in smaller scales, and especially with lots of convection. Another issue is that the ocean can change. We've seen that this year in 2016, the first few storms in the East Pacific, Bloss and Celia, having tracks right over one another, and now the latest one is going over the same tracks as again, because the hurricanes upwell cooler water from below. And so knowing what the sea surface temperature is and the structure down to the thermocline is very important. And then finally, the global models don't provide perfect synoptic scale predictions. They tend to get less skillful over time. So one way around having sparse observations is to use a technique called Bogussing, where you insert a synthetic vortex into the initialization of the model and use that to going forward in time to look at the track and the intensity forecast. It used to be used a lot more in the past, but people are moving away from Bogussing because it causes problems too. It's often difficult for the mass field to relate correctly to the surrounding synoptic field when you're inserting a bogus vortex. And also, when you insert this, you're going to be removing some real component from the atmosphere, and so you may affect the vertical shear, for example. And we've also seen that storm models that have bogus vortices in them, they tend to be a little too resilient to vertical shear as well as the extratropical transition. So as an example, even at the initial conditions, the vertical shear can be quite different. But between the global model, that is the parent model being used, the GFS, the GFDL that implies a bogus vortex every time, and the HWRF, which doesn't use a bogus vortex, it actually uses a first guess from the previous run. But all these analyze the vertical shear a little bit differently, and sometimes large differences, and that's at the initial time. So as you integrate forward in time, the differences between the global model and the embedded regional models grows. So one way to describe different models is to say, well, roughly how much resolution they have. That is, what are the finest scale features that they can depict. And so you may have ones that are indicated to be, for example, triangular truncation, which is how many waves around the world is it representing the atmosphere. Others may use grid point models. And so an example here, to calculate the approximate horizontal resolution from the model, you come up with this formula here, and for a case where you've got triangular truncation of 400 waves, this would roughly equal about a 33-kilometer grid spacing. So that used to be incredibly fine scale 10 years ago. Now it's standard or a little worse on the global scale. And for mesoscale models, it's very common now to get all the way down to 2 or 3 kilometers. So these are some of the global model properties. I'm not going to go into this in detail, but it's important to point out that we at the Hurricane Center don't rely on a single model. We're relying on independent models that have different data assimilation, different assumptions about physics, and it's because there's no perfect way to depict things. Having independent model output is very important for us till we get a sense of what the uncertainty is. And just to point out at the end, for these 5 global models that we look at routinely, the Canadian, the EC, and the UK do not bogus any longer. The Navy's NavGem does insert a bogus, and the GFS does not bogus, but it does relocate the vortex to the correct location as information at the Hurricane Center. So a little more detail about the GFDL mesoscale hurricane model. This has been around for about 20-25 years as well, and it's had multiple versions where they've been upgrading it, mainly due to the work of Bob Talea and Morris Bender at the Geophysical Fluid Dynamics Lab in Princeton. So this coming week, so the last half of July, we have a new version of the GFDL that's going to be released soon. The nesting approach is it's one-way nesting. So the GFS provides the initial conditions everywhere, and it also provides the boundary conditions on the sides. And so it's a one-way nesting technique. So information comes in from the GFS, but the output from the GFDL model does not go out to the global model. So it's a one-way nesting technique. And they've got 3 grids, and the innermost one has a resolution currently of 6 kilometers. So it can't quite run explicit convection, but it's also a hydrostatic model, so you're kind of reaching the limitations of what a hydrostatic model can do. So this shows an example of, for example, a hurricane that would be getting close to the Yucatan of Mexico, what the 3 meshes would look like for this, where the most fine detail is reserved for right over the storm, an intermediate mesh in the periphery, and then a coarse mesh on the outer side. So some of the upgrades that were made for this year were to upgrade some of the model physics, both the microphysics, the convection parameterizations was changed a bit, and also folks at GFDL tried to better represent the initial wind profile, that is both in the vertical as well as in the horizontal of what the swirling circulation looks like. They're also changing the ocean coupling, so it used to use the Princeton ocean model, the POM model, and now they're switching to what's called the real-time ocean forecast system model. And they've also made assorted fixes as well. And so we're hopeful that the improvements will bring GFDL back up on par with the other guidance for 2016. HWRF is the most recent development for hurricane mesoscale models. It's been in place for about just about 10 years now operationally. It also has 3 nested grids, and the innermost grid has a resolution down to 2 kilometers. So they can actually do explicit convection instead of parameterized convection with this. It uses the Princeton Ocean model in the Atlantic and East Pacific, and instead of a cold start every time where they insert a bogus vortex, they actually use the previous model run and use the 6-hour forecast information as the first guess for the initialization. So that really helps in having a balanced vortex in the model. They do have a data assimilation scheme in the HWRF, whereas GFDL does not. And so they're making more use of aircraft data. So now whenever there's a Doppler mission from one of the Orion P3s from the Aircraft Operations Center, they'll get that Doppler radar information and incorporate that into the data assimilation. And this year they're going to try to also use any land-based Doppler radar. So this runs in parallel with GFDL and HWRF. So they're not run 365 days a year. They're only run on request by either the National Hurricane Center or the Central Pacific Hurricane Center. So this gives a couple cartoons of the grid system and what it might look like from representation of the precipitation from the HWRF model and the surface winds and the convective structure. So it's getting to be more and more realistic. Doesn't always mean it's a great forecast, but the output is becoming much more lifelike. So the upgrades this year, and a lot of this is through funding from the Hurricane Forecast Improvement Program. So the resolution, increasing the sizes basically of the innermost meshes. They're upgrading some of the dynamics, going to a 30-second time step. And they're upgrading the data assimilation some of the ocean wave coupling, and the model physics. So they're doing a huge amount of testing during the off season. And next week, along with the GFDL model, they'll be implementing the 2016 version of the HWRF. So this table gives you a little flavor of some of the details of what is being used for both the HWRF model and GFDL model, if you're interested in some of those details there. So one thing to keep in mind is, well, how does the Hurricane Center use models, and which ones do they look at, and how do they take into account that, for example, the 12Z model, it's not going to be ready instantaneously. So, for example, the global models, we usually get the GFDL, Global Forecast System model, about 4 to 5 hours after synoptic time. Problem is, we issue advisories 3 hours after synoptic time. So by 15Z, or 11 a.m. Eastern time, we're issuing an advisory. So we can't use any of the 12Z global models or regional hurricane models. So we have to use the last one that was available. So what they do is the ones that are not available at synoptic time, and again, it's all the dynamical ones, they're called late models. Can't use them for the current forecast. So what we do is we take the previous one, run from that model, and adjust it for the 6-hour position, so where we know it's at now. And then that process is called an interpolated version for historical reasons. So that's done for all the global models and the regional hurricane models. There are some early models, so all the statistical dynamical models are early models. There is a barotropic model that's run fast enough it can be considered earlier, and there's a beta and advection model that's also available right away. So the consensus techniques. So this is the fourth flavor of different models. Again, you have the basics, climatology and persistence. You have the statistical dynamical ones. You have the pure dynamical ones. And then the consensus. And this is blending together output from different models. So there's 3 different ways that this is done. One is to take just the 4 models, the 2 statistical ones, Decay-SHIPS, LGEM, and the 2 regional hurricane models, GFDL, but it's got a different acronym here. I'm not going to get into why, and the HWRF. So just add those up, divide by 4. And that's done every time that all 4 of those models are available. This year, we have a variable consensus technique, IVCN, Intensity Variable Consensus. And it has those 4, but it also adds the Navy's COAMPS TC model, because it's performed very well over the last few years. And so adding it into our mix allows for a better prediction. Lastly, there's a Florida State Super Ensemble technique that's been made available for the last several years, and sometimes it outperforms the variable consensus model, but sometimes it does not do better than just add these 5 up and divide by 5. So it struggles to improve upon a simple average. And I think it's because the models keep changing. So the characteristics, the biases that this Florida State Super Ensemble are trying to correct for, it's a moving target. And so it makes it very difficult for this Super Ensemble to really be super. So here's an example from Hurricane Ike. It's a few years old, but it's very, very relevant today still. Initial intensity was judged to be 115 knots. It's Category 4 condition. And this was when it was east of Florida. And the white hurricane symbols are what actually occurred. So it ended up weakening and then re-strengthening a little bit. And you can see how the models can have huge divergence here. So the lowest of which was Decay-SHIPS, which suggested it would only be a minimal tropical storm, 35 knots. The LGEM statistical model showed weakening and then rebounding. The GFDL hurricane model showed similar and probably the best forecast. And then the HWRF was showing all the way to 145 knots. So that's a range of 110 knots of plausible solutions. So this is extreme, but it does give an idea of what can occur in operations, because the model skill is still quite low. So it's not that uncommon to have extremely diverse forecast solutions. Of note, the IVCN, this dark blue, did really well. So in this case, it was the consensus technique turned out to be an excellent forecast. So it's important every year to verify our forecasts as well as the model forecasts. And so when we do these verifications and we're comparing models, we want to make sure it's an apples-to-apples comparison. So we want to make sure that it's the same number of cases for each models. And also, we do verify if it's a tropical cyclone or a subtropical cyclone. But once it becomes extratropical, we don't include those in the stats. We can if we want to, but we generally don't. And then, as I mentioned before, the SHIFOR, Statistical Hurricane Forecast System, is the baseline for the intensity. And so if you improve upon it, then you have positive or you have skill. So that's what I'm going to show you next. So over the last 5 years, and this is for the Atlantic, Caribbean, and Gulf of Mexico, and these are the early models, so it's the interpolated late models for HWRF and GFDL, and then the two statistical ones, Decay-SHIPS and LGEM. And OCD5 is the SHIFOR, that's the climatology and persistence. And then our official forecasts are in black. So this is a homogeneous fair comparison, 5-year sample, so there's at least a couple hundred samples at the initial time. And you can see the air characteristics. At the initial time, we don't start at zero, because after the storm is done, we do a post-storm assessment, and we also assess the intensity at each 6-hour period. And so in this case, on average, we adjusted the intensity from the initial time by, say, on average of 2 or 3 knots. So that's some of the uncertainty in knowing how strong a storm is. And you can see that the intensity grows fairly quickly at first through 48 hours, and then by 72 and 96 hours, it kind of starts tapering off. And that's because it's a bounded problem. You're never going to have 150 knot air because of the thermodynamic limitations and how strong a storm can be. So essentially by about 4 or 5 days, you're about as bad as you can get. The errors aren't going to increase generally. And when you look at which models are best, it's a little easier on the right side to intercompare them. So in this case, we're looking at a skill diagram. So on top is percent error in knots, less than SHIFOR, and on the bottom is percent error worse than SHIFOR. So you don't want to be down here. You want to be up here. If we look at the statistical models first, they generally have 5 to 10% skill above SHIFOR. It's not a lot. It's tough to show a lot of skill for intensity prediction. And you can see LGEM does a little worse than Decay-SHIPS, and a little better or about the same at the longer time periods. So the dynamical model is very different. They show more skill, especially the HWRF model, at 24 and 48 hours, but then their skill drops way down and actually goes negative at days 4 and 5. So our forecasters take the blend of these 4 and come up with the official forecast. And it's good because it means they're providing value-added information and making a better prediction. In this case, the skill is about 20-25% better than a simple climatology and persistence. Not great, but still an improvement there. So what about last year? Last year was not super busy for most of the year, but we did have Joaquin, which is a big storm and a lot of impacts in the Caribbean. And in this case, we're also including a few more models. The GFNI that I mentioned, that's the Navy version of the Princeton model. And it also has 2 of the global models, the GFS in dark blue, and also the European Center in light blue. Because we do want to see if the global models are starting to help with intensity forecasting, despite their lack of fine-scale resolution. And what you see, at least for those two models, is they start off negative, that is worse than climatology and persistence, but especially by days 4 and 5, the global models showed substantial skill last year. And so we're going to be increasingly taking at least a look at those global models going forward. The statistical ones, dark red and dark purple, showed quite a bit of skill last year, all the way to about 40% skill level. And then the other dynamical models, the GFDL, GFDN, and HWRF, well, it's a little different. So GFDL, GHMI in this nomenclature, showed a little bit of skill, and then it tanked. It really did poorly at days 4 and 5. And we recognized that pretty early on and did not emphasize it in our predictions last year. The GFNI actually surprisingly did a little bit better at the longer ranges. But clearly the best single model last year was the HWRF. You can see up here in pink it had the highest skill levels. It was in general comparable with the statistical techniques. Those three really did the best. And then blending them together, you have the variable consensus. So that's just take the best 4, add them up, and divide by 4. And it was the best technique early on, and it was about the same as the statistical ones. Then it did worse because the GFDL pulled it down. The Florida State Super Ensemble did improve over a simple consensus out through 36 hours, and actually improved upon that at days 4 and 5. And again, our official forecasts are right at the top or a little better than the best techniques available. The Eastern Pacific, the other basin that a lot of folks don't realize we forecast for, a similar kind of approach. The global models, here's the EC model, here's the global forecast system, either very limited skill or negative skill. The 3 dynamical models, the GFNI, not a good player there. The GFDL model also had a lot of problems, but the HWRF in pink showed quite a bit of skill, especially days 3, 4, and 5. But in this case, in East Pacific, the statistical techniques were the best approaches. Now, it's curious to see how these change over time, because all the techniques, whether it's the dynamical models or the statistical dynamical ones, are improved upon. So folks spend a lot of time to upgrade these models in the off-season, and that's great because this competition leads to better tools for us at the Hurricane Center and better predictions that we can provide to the public. So you look back over time, in dark blue are the statistical dynamical models. And you can see for the majority of the years, statistical dynamical models were best, especially at a shorter time forecast of 2 days. But you can see where the red ones, where you're starting to get some of the regional hurricane models, whether it's the GFDL model or the HWRF starting to show up. And occasionally, and I think these are more flukes, where the global models were the best performers for that particular time period, for that particular year. So it's, and we don't care which is the best model. If we can recognize that it's performing well for the season and emphasize it, then that's what we would try to do, especially through the consensus techniques. So rapid intensity. A special problem that we have is for storms that very quickly spin up. So an increase of at least 30 knots or 35 miles per hour in 1 day. That's about 2 categories on the Saffir-Simpson scale. It corresponds to 5% of all tropical cyclones have a time period. Well, during the life cycle of all tropical cyclones, 5% of the time they go through rapid intensification. And so this example here, where it did 160 knot intensification from a minimal hurricane to a Category 5. So trying to get this with dynamical models is extremely difficult, if not impossible, because of how tiny the eye becomes when it gets this strong. So there's a statistical techniques that provides probabilistic guidance, and it's using much of the same predictors that go into SHIPS and LGEM, and they provide probability of rapid intensification for 4 lead times, so a half day, 1 day, day and a half, and 2 days. and they have different thresholds for each of these naturally. And it's using a lot of the same physically based predictors that go into our regular guidance. So the way that we look at it, so for example, for Patricia last year, which was an extremely rapid intensifier, we look at the 30 knot percentage. It was 99% chance of having that rapid intensification. So extremely quick. Even a 40 knot change had a 98% chance. So we've never seen numbers this high before. And of course, it did extremely rapidly spin up. Again, the Rapid Intensification Index and the SHIPS models all available to the public on that FTP site. So how well did this Rapid Intensification Index work? There's a couple different flavors that use somewhat different statistical approaches, and they do have skill relative to climatology as measured by a Brier score. And so these are evaluated every couple years, and they do have enough skill that if we start seeing values, say a 30% chance or a 50% chance or a 70% chance of rapid intensification, that'll allow us to bump up our numbers on the intensity predictions somewhat subjectively. We'll skip this one. So, are we getting better? And the answer is yes. We're actually improving the intensity forecast, especially for 3 days and beyond. So if we look at, for example, the 3-day forecast, and this is the yellow line shows the long-term trend. Back in 1990, we had an average error for a 3-day forecast of about 21 knots. And now that's all the way down to about 16 knots. So a substantial reduction in 25 years. You can see we've had what looks like a really sharp drop in the errors, especially for days 3 to 5. But some of this has been, we've had some pretty wimpy hurricane seasons. And if you don't have Category 4 and 5 storms, your errors tend to be limited. And so that's partly why we've had smaller errors, except for last year. The errors went back up, and part of that was Joaquin and the unexpected of it unexpectedly becoming a Category 4. We see similar error characteristics in the East Pacific, where the longer-term intensity forecasts are improving. And again, I would say that some of these improvements are based on the work funded through the Hurricane Forecast Improvement Program and the Joint Hurricane Testbed. One thing to take a note, though, is that the one-day forecasts really aren't getting any better. And that's partly because of we can't sample them perfectly at the initial time. So our uncertainty of the initial intensity is about plus or minus 10%. So if we say something is a 90-knot Category 2 hurricane, given the errors involved in estimating the intensity, it could easily be an 80-knot Category 1, or it could be a 100-knot Category 3. And so until we get better ways to measure intensity and the wind structure of hurricanes, it may be difficult to substantially reduce the one-day errors. If you look at it in skill score, that is better or worse than simple climatology and persistence. The zero line's kind of riding right through here in the Atlantic, and you do see, in general, upward jumps in the skill. Some years, not nearly as much, and sometimes these follow years where it was a real busy one last year and everything formed and rapidly intensified, like 2005. So when 2006 came around, maybe our models and maybe our forecasters were expecting that to continue, and turned out to not be a skillful year for intensity forecasting. Same thing in the East Pacific. It's fairly noisy, but it does show in the last 7 or 8 years improvements in the skill for making intensity forecasting. So that covers the intensity prediction, which is the maximum wind. I did want to mention a couple things about surface wind structure. That is the extent of tropical storm force winds, 50 knots, and hurricane force winds. We do an analysis of that by quadrants, and it's the maximum radial extent in that quadrant of each of these 3 wind thresholds. So we don't have a full 2-dimensional depiction. It's a fairly crude rendition, and it's in part because we typically don't have a lot of observations to better specify the wind structure than this fairly crude depiction. So we make a wind forecast of the radii out to 3 days for tropical storm and 50 knots, and only out to 36 hours for hurricane force. And again, it's because if we can't better measure what's going on now, we're reluctant to extend the forecast out beyond what we're doing currently. Knowing the structure is very important, though, because, for example, if you have 100-knot hurricane that's very tiny, that'll produce very little storm surge when it comes ashore. But if it's a 100-knot hurricane with a gigantic hurricane and 50-knot wind radii, the storm surge may be double or triple the size. So, of course, a larger storm is going to provide more wind damage and potentially more rainfall as well. So this shows a comparison of two types of hurricanes. Hurricane Dolly, so the brown shows the extent of hurricane force winds, very, very limited, versus Ike, which had a much larger hurricane wind radii. So I mentioned a little bit about the limitations because we don't measure things very well. So when we're looking at forecasts, partly we don't understand the processes that control storm size really well. That is an active area of research to try to understand what determines if it's going to be a large or a small storm over time. We do have statistical techniques, climatology and persistence wind radii. We do know that as a storm is later in its life cycle, that it tends to become larger, especially if it's undergoing extratropical transition. The wind field will spread out. The global models can't pick out the inner core at all, so they're worthless for getting 64-knot hurricane force wind radii. They do provide some guidance for the tropical storm force winds. The regional hurricane models have the potential for providing hurricane force winds, and we're still trying to better validate these to see how much we can rely upon them. So this provides an overview today about one of the aspects that we forecast, intensity, or maximum surface winds, and a little bit about the size as well. This is just one of the things we provide, every 6 hours with a new advisory, in addition to the track storm surge within about 2 days of landfall. Rainfall forecasts are included in our public advisory. Those are provided by the Weather Prediction Center. Any potential for tornadoes is provided by the Storm Prediction Center. And we'll include where the real high seas are for mariners to stay out of the way of tropical storms and hurricanes. And that's provided by the Tropical Analysis and Forecast Branch at the Hurricane Center, as well as for the Ocean Prediction Center for north of 30 degrees latitude. So just to wrap up, intensity forecasting is improving. It still doesn't have a lot of skill, and that's not because we have some dumb forecasters. We just have models that are limited. And I foresee that we're going to continue to have a blend of statistical techniques and dynamical models for at least the next 10 years. So having a variety of models is very helpful, a variety of approaches, and trying to determine the biases in some of them and removing some of the biases either empirically or more objectively is great. And again, there has been quite a bit of funding available in the last few years through the Hurricane Forecast Improvement model, project to improve especially the HWRF model. So I think I'll stop there. And there's more websites if you want to get more of the gory details about all these different models. And